And good afternoon, everybody. Here are your notes for section packet 3.9, and it's going to be talking about differentials and linear approximation. Kind of the big idea for this is we're going to be using the first derivative, f prime. So we're going to be using the first derivative, or in this notation, dy dx, we're going to be using the first derivative to approximate certain values. And let's go ahead and look at the first example. So this one is what they call linear approximation. So we're going to be using a straight line to represent a curve, and we're going to use the straight line to approximate the output on the curve. So if we were to choose a point of tangency on the curve, let's say right here, and draw in the tangent line, as long as we stay relatively close to this curve, the outputs on the tangent line are going to be very close to the outputs on the curve. So if our curve was f of x, and the tangent line, we'll call it t of x for tangent. So if our tangent line was t of x, as long as we stay in a relatively small area, close to the point of tangency, then the outputs on that straight line are going to be very close to the outputs on the curve. So here's their example. We have some function f of x is equal to 1 plus sine of x, and they give us the graph below. And they want us to find the value of f of 0.01. So if we took their original function f of x, and they want us to find f of 0.01, it's going to be 1 plus the sine of 0.01. And here's where the tangent line and the approximation comes in. Let's suppose that you didn't have access to a calculator or a computer to go find what the sine of 0.01 was. Let's say you were limited in technology and you had to do this all by hand. You could get an estimate by using a tangent line. So what we're going to do is build our tangent line at this point of tangency. So to make a tangent line, you need two things. You need a point and a slope. The point, if we look at the point of tangency is going to be at 0, 1. So that's the point on the graph. And the slope is going to come from the first derivative. So we need the slope at this point. So we'll take our function f and find f prime. So the derivative of f, the derivative of 1 is 0, derivative of sine is cosine. So we now have a first derivative, and the job of the first derivative is to tell us what the slope is at a single point. The point that we want is where x happens to be 0. So we'll put that into our first derivative. So what is f prime at the x value of 0? Cosine of 0 should be 1. So that's telling us that our slope at that point is going to be a slope of 1. And now we can go ahead and create the equation for our tangent line. So if we use our point slope form, y minus y1 equals m, x minus x1, and put in the known information. So y minus, what's the known y value? So the known y value is 1, equals, what's the slope? We found the slope to be 1. x minus, what's the known x value at this point? That's going to be 0. And once you have the equation in point slope form, you can go ahead and simplify. So we have y minus 1 equals 1x. And you can solve for y. So it's going to be 1x plus 1. So there's the equation of our tangent line. If you wanted to put it into function notation, we could call it capital T for tangent. So the equation of the tangent line is x plus 1. And this tangent line should approximate the curve around that point of tangency. So the original question was, what is f of 0.01? And without a calculator or without a computer or something to tell you what the sine of that small angle 0.01 is, you would have a tough time doing that. But you could use our tangent line to get an approximate. So if we're looking for the output at 0.01 on the f function, it should be very close to the output on the tangent line. So we can put this into our tangent line. So we'll say that tangent with an input of 0.01. What do we get for an output? That's going to be an input of 0.01 plus 1. So t of 0.01 should be equal to 1.01. So that's going to be our estimate for the output on the curve. So that is the output on the tangent line. That's going to be very close to the output on the curve. And just to kind of see how we did, let's go ahead and actually do the actual output on the curve using a calculator. So let's make some room here. So back to the original question, what is f of 0.01? So if we did this on an actual calculator, and we did 1 plus the sine of 0.01, just make sure you're in radian mode. If you were to work that out on a calculator, it should work out to be approximately 1.00999833. So notice this value, the actual output on the curve, is very close to the output on the tangent line. So the tangent line output was 1.01. If we round to the second decimal place, we have a 9 here. So if we rounded that to the second decimal place, that's going to be 1.01, which is the same as the output on that tangent line. So linear approximation is essentially using a straight line to represent a curved line, and the outputs on the straight line are going to be very close to the outputs on the curved line near that point of tangency. If you get further away from the point of tangency, obviously the output on the line is not going to be very close to the output on the curve. But as long as you stay relatively close, right around that point of tangency, they should be very similar to each other. The second part of the notes is going to be talking about differentials, and a differential is going to help us find the change in the output, or the change in the y value. And for finding the change in the y value, when you have a known change in the x value, if you look at your dy dx form of your first derivative and think about what that is telling you, dy over dx, the top part is speaking about the change in y. So the change in y, if you remember where it originally came from when we were first developing the concept of a first derivative, it came from a slope calculation, delta y. So the dy is standing for the change in y at a single point, and this is talking about the change in x at a single point. If you put the two together, then you get the slope at a single point. So dy over dx is the slope at a single point. If we were just concerned about the change in y, when we know what the change in x is, then we could rewrite our first derivative and get a new equation that would tell us what the change in y is going to be. So for example, if I had an equation y equals 5x squared plus 2x, and let's say I wanted to know what the change in y was going to be if I changed the x value by a certain number, we could take the derivative and we're going to get the derivative of y, so dy dx is equal to, and we'll derive this side, 10x plus 2. And if we left it in this form, then if we put a number in for x, it would basically be calculating the slope, dy over dx. But if we were only interested in how the y was changing, when we knew how the x was going to change, we could rewrite this equation. We could multiply both sides by dx and essentially bring our dx over to the other side. So if we multiply both sides by dx, if you multiply the left side by dx, then it's going to cancel and you're left with dy. And then whatever you do to one side, do it to the other side. So multiply this side by dx. You're going to get a rewritten form of that first derivative. And this is going to be representing the change in y when we know what the change in x is. So if we knew what the x was, and we knew how much we were going to change x by, then it's going to tell us how much we should expect y to change by. So here's our first example. So we have the equation y equals x squared, and they want us to determine or estimate the change in y using a differential. When we know the x, the first input for x is going to be 1, and we're going to change that input. So the delta x is going to be 0.01, so we're going to change the input by 0.01. So let's use differentials first, and then they're actually going to have us go find the true change in y. So if we have the equation y equals x squared, the change in y with respect to x will be 2x. And we're interested in just the change in y, so we're going to multiply both sides by dx. So this will be our differential. And we are interested in the change in y when we know what the x is and we know what the change in x is going to be. So how much will y change by if we have an x value of 1? So they said x was going to be 1. So the x value is 1, and the change in the x value, the dx or the delta x, is going to be 0.01. And if we work this out, we have 2 times 1 times 0.01, so that should get you 0.02. So what this is essentially saying is if we started with an x value of 1 and we changed the x value by 0.01, we should expect the y value to change by about 0.02. So that would be approximating or estimating the change in y by using a differential or a first derivative. Then they want you to go ahead and compare it to the true or the actual change in y. So to find the actual change in y, you pretty much just need to do it from start to finish. You need to take your equation, y equals x squared, determine what the output is when y or when x is 1. So 1 squared should get you 1. So that is the first output. And if we change our x value by 0.01, so we're going to have a 1, but we're going to change it or add 0.01 to it. And if we compute that, it's going to be 1.01 squared. And squaring that out, we should get 1.0201. So this was our first output. This was our second output. What is the change in the outputs? The change in y. The change in y would be y2 minus y1. So what was our second output? That was the 1.0201 minus, what was the first output? 1. And if we subtract, we should get a change in y is equal to 0.0201. And notice the true change in y, or the exact change in y, is very close to the estimated change in y. So you can use a derivative or a differential to estimate or predict about how much your y value will change when you have a change in your x value. So in summary, on the left side, this is using calculus to estimate how much your y will change by. So this is an estimate using calculus. And this would just be using basic algebra to find the exact change in y. So here's an example of an application. So we have the radius of a ball bearing is measured to be 0.7 inches, and the measurement is correct to within plus or minus 0.01 inches. So a ball bearing is going to be a small ball or a small sphere. And what they are saying is if we have this ball bearing and if we measure the radius, so the r value, so that's going to be our radius. What they're saying is the radius is measured to be 0.7 inches. And the change in the radius, so when they measure this, they think it's 0.7, but they know that their measurement could be off by as much as plus or minus 0.01. So that's going to be their measurement error. So if they were to have this measurement error, they're asking you how much is that going to affect their calculation on the volume. So they want you to find the change in the volume. So let's go ahead and use our first derivative to estimate this. So the volume of a sphere is 4/3 pi r cubed, and we want to produce a first derivative with respect to the change in r. So derive it with respect to r. So the derivative of v should be 1, and then it's going to be a dv dr equals the first derivative of this. Your 3 is going to come down. The 4/3 pi is all a constant. So your 3 comes down off the r cubed, and then drop it down a power. And simplify, your 3's are going to cancel, top and bottom. So your change in volume compared to the change in the radius would be 4 pi r squared. And we're not interested in the ratio between the change in the volume and the change in the radius. We are just interested in the change in the volume. So we can bring the dr to the other side. So the change in the volume can be found by doing 4 pi r squared multiplied by the change in the radius. And here we can use our given information, so we're looking for the change in the volume. 4 pi, what is the r value? So it's assumed that the r value was 0.7, so that's going to go in for r. But we also know that it could change by as much as 0.01. So we'll put that in for the dr, the change in r. And then we can go ahead and compute this. Alright, sorry about that. I think I had the pause button hit at certain points in time. So we found the change in the volume by using our differential. And if you multiply the pi in, then this would be the decimal approximation. So our volume is going to change by approximately plus or minus 0.0615 cubic inches. They call this the propagated error, just the amount of error. The next question is, how much error is that relative to the size of the sphere? So if this was a big sphere like a beach ball, this change in the volume might be rather insignificant, kind of a small change in the volume compared to the size of the object. But if it's a really small object, then this 0.0615 cubic inches might be kind of a big change in the volume, so a significant change in the volume. So what we want to do is find what they call the relative error. And the relative error is going to compare it to the size of the object. So it's going to take your known change and compare it to how big the object is in the first place. So relative to the size of the object. So we're going to take our dV, our change in volume, and we are going to compare that to the actual volume if the radius was actually truly 0.7 like what they measured it. And then we're going to need some more space, so let's go ahead and take our work over to another page. So again, here is our change in volume, the 0.0196 pi if we don't multiply in the pi, and we're going to look for the change in the volume and compare it to the true volume if the radius was the true 0.7 that they measured it at. So the change in volume is the 0.196 pi divided by the actual volume, so we're going to need to use our volume formula, 4/3 pi r cubed. So we're going to put this in 4/3 pi, what is r assumed to be? 0.7. So 0.7 cubed and oops, I got a typo in the numerator, so it should be 0.0196, not 0.196. So let's fix that. So we need a 0. So 0.0196 pi was the change in the volume, and we're going to compute the true volume if it did have a radius of 0.7. So let's go ahead and compute that. So you can do the 0.7 cubed times the 4 divided by 3. So up top we're going to have 0.0196 pi, and down bottom it works out to be 0.457. 3 repeating pi, if you don't factor in the pi. So if you don't have the pi factored in on both the top and the bottom, the pi's kind of conveniently cancel. So we're left with a ratio of 0.0196 divided by 0.4573 repeating. And if we work that out on a calculator, it should be approximately 0.0428573 1429, whatever you want to go to for decimal places. So there's the approximate relative error, and even this number doesn't speak too much, or it's kind of hard to imagine if that's a big change. So what we can do is actually turn this into a percent change. So we can take our relative error, so the amount of error that is relative to the actual size of the ball bearing, and if we multiply that by 100, then we're going to get the percent form. So if we multiply it by 100, that's going to move your decimal 2 spots to the right. So that's going to get us approximately 4.29%, depending on what you want to round to. So that's a little bit more clear as far as how much the change in the radius affected the change in the volume. So if your radius was able to change by as much as plus or minus 0.01, then you would expect your volume calculation to be off by as much as plus or minus 4.29%. And again, that would be plus or minus. So your volume will be off by as much as about 4.3%. And that should be the notes for section 3.9, discussing linear approximation and how to use differentials to approximate a change in a output or a change in a y value.